third and the last presentation of this session, which will be given by Professor Oliver Kroemer from University of Carnegie Mellon University. And Olivier, yes, okay. So I will give a quick introduction to Professor Oliver Kroemer. He's an assistant professor with Intelligent Autonomous Manipulation Lab of the Robotics Institute at Carnegie Mellon University. Before joining the CMU Robotics Institute in 2018, he was a postdoc researcher at the University of Southern California. He received his master and bachelor degree in engineering from the University of Cambridge in 2008. From 2009 to 2011, he was a PhD student at the Max Planck Institute for Intelligent Systems. In 2014, he defended his PhD thesis at the Technical University Darmstadt and was a finalist for the 2015 George Giraud PhD Award for the best robotics PhD thesis in Europe. His research focuses on developing algorithms and representations to enable robots to learn versatile manipulation skills over time. So, Professor Kroemer, yeah, you are ready.
Yes, thank you for the introduction, and thank you everybody for joining. Very happy to be here and see everyone. All right, so today I'm going to be talking about tactile sensing and dexterous deltas for food manipulation. So my lab is very interested in the idea of having robots be able to prepare healthy foods for people of all ages. So I think, one of the reasons fast food has become so popular is because it is just so convenient. And, we're hoping to sort of make the healthy equivalent of that by making autonomous food preparation. Obviously, there's a lot of different challenges when we look at actual manipulation of food items. So we need to be able to identify different types of food. We need to be able to adapt to their material properties. There's various different kinds of skill that we need. So we need cutting, we need plating, we need actual stirring, being able to drizzle maybe some cheese on top of this salad would be amazing. And so it's obviously a very rich environment for lots of different kinds of manipulation tasks. So we're very excited about this sort of application domain. And the talk I'm going to give today is going to be looking at sort of two key areas that we've been looking into. The first one is kind of the tactile sensing side, and how we can sort of identify different kinds of food materials. And the second one is actually looking at a little hardware design and how we can sort of make dexterous grippers and showing a little bit of how we can use them for food manipulation. To begin with, though, I want to talk about vibrotactile sensing for food. So whenever I think about manipulation tasks, the first thing I always think about is manipulation modes, right? So we have this sort of natural structure to any manipulation task where we have different kinds of modes. So for example, here we have different ones for grasping. Depending on which mode we're in, we can perform different kinds of interactions with our environment. So here we can just move our hand. Here we can apply forces. Here we can move this object around. Or, alternatively, we can sort of slide the object across the surface if that's what we want to do, okay? And in order to sort of monitor the different modes, we often sort of rely on vibrotactile feedback. So when we're making contact, when we're breaking contact, or when we have sliding contact, these are often good indicators of a mode transition happening, whether it's something that we want. So maybe if we want to just pick it up, then this mode transition becomes an error, or if we want to actually slide it, then this mode transition here becomes sort of a goal, and that scraping sound is actually something that we want. Now, obviously, we want to take this further, this idea, than just for grasping. So here you can see kind of what the manipulation modes are for cutting. So we first make contact with the side of the knife, the side of the vegetable with the knife. We're then going to move down until we make contact, at which point we start slicing through it until we actually reach that cutting board. At that point, the sound is going to change dramatically. Because we're now cutting into wood effectively. You can see here on the back of the knife, there's a little microphone there. We have another one over here, and we have three underneath the cutting board. And so we've actually looked at training neural networks in order to identify the different kinds of events. So when it slips off, when it starts cutting, when it bumps into the object, and we can sort of, control this high-level switching of behaviors depending on those vibrotactile feedback. What we're interested in, though, is not just detecting when those contact events happen, but getting additional information from them. In particular, we want to be able to extract material information from these kinds of manipulation skills. And in particular, what we've been focusing on is that initial contact with the food item. So when we take our knife and bring it down, we make contact with the object, and we have a very small window where we sort of get some additional vibration feedback regarding the actual material. Okay, and so what we want to do is we want to take those vibration signals detected by the microphones and use those to actually classify the type of food item that we have. And to do this, we gave the robot, I think it was 26, I think we have 25 here, different food items to classify. So we have things such as zucchini, cucumber, old cucumber, which is the same as a cucumber, but it's left in the fridge for a week. We have oranges, lemons, and frozen lemons, an old tomato and a normal tomato or bell pepper. So visually, some of these are very similar, but we want to be able to sort of identify what kind of food item we're interacting with based simply on those vibration signals. And the first thing that we do is we take that small window of vibrations and we compute the Mel frequency cepstrum coefficients. So for those of you who are not familiar with that, it pretty much means we take the signal, we take the power spectrum of it, and then that power spectrum, we take another power spectrum of that. What this does is it allows us to capture the sort of harmonic structure of those vibrations, and intuitively we can think of that as kind of the timbre of the sound. So if you hear a brass instrument and a woodwind instrument playing the same note, it's the harmonic structure which makes them sound different. And in this case, we're playing tomatoes versus cucumbers rather than brass versus woodwind. We then take those features, put them through a fairly straightforward, fully connected and multi-layer perceptron. We got three layers, 100 units each, and then the output is these 25 different food classes. And here we can see the confusion matrix when we do this. So we actually, we're only showing the errors here. So obviously it's a 25 by 25 grid usually. Most cases it is actually getting them perfectly correct. We can see some confusions here. So for example, it's a bread. I thought it was an old tomato, or a watermelon. I thought it was a frozen lemon. Again, we're not using any kind of visual cues here. This is all simply based on those vibration signals. And using that small amount of data, which is very rich data though, we can actually get an F1 score of 0.99 out of 1. What we can do then with this is we can actually define for different kinds of vegetables, different cutting parameters, and have the robot identify what the vegetable type is and then select the corresponding parameters. So here you can see some examples where the robot's correctly classifying different kinds of vegetables and then adapting its parameters accordingly. So for the old tomato, we gave it parameters that do a lot less pressure, a lot more back and forth, whereas with the carrot, it's applying a lot more force to go straight down. Of course, these are examples where we have a food type and we sort of, we're applying our network to an existing label. What happens if we give it new food types that it hasn't seen before? So in that case, we're forcing it to find a different material that has similar properties. So up here, for example, it doesn't know what a peach is, but it thinks it's kind of similar to zucchini. I mean, if you've ever sort of cut into a very unripe peach, you can kind of imagine how that's similar. Similarly, it doesn't know what a pear is, but it does know what an apple is. So it's going to take the parameters from the apple, which are obviously very similar. And then finally here we have jalapeno, which again, it doesn't know. And visually you might think, oh, this looks more like a cucumber or something like a small pickle. But it accurately says that the material properties of this are much more similar to a bell pepper. So you have that nice sort of cell structure, very watery material, and it's being able to identify that simply based on these vibration signals. So this project was very exciting. We wanted to see sort of how we can extend this idea of sort of learning representations using this vibrotactile information. And we were very excited about the idea of kind of doing a developmental approach. So having a robot kind of play around with food and learn kind of visual representations of it based on the interactions it has. So ultimately, we're still, so in this case, we're actually trying to learn a visual representation. So some kind of an embedding of a picture of a slice, for example. So here we want to take this picture and embed it as a vector, which we can then use for classification. But we want to be able to learn this kind of representation through interaction. So we have this idea of interactive learning, where we're using interactions to train the vision system. So obviously we need some data. So we set up the robot to perform some playing actions. So we grasp the object, we pick it up, we drop it, we move our hand down on top of it to crush it. And during these operations, we're collecting a variety of different data. We have vision data, both from the outside and from within the fingertips. We again have microphones on the cutting board and on the back of the fingers, so we can detect those. And we also have some proprioceptive and haptic features, such as the forces and how much the fingers close or how far down our hand goes. So we tried this on a whole variety of different vegetables and fruits, also looking at different shapes of objects, so different kinds of slices. We had the robot sort of cut different kinds of slices with different parameters, so we could also give it some slice information. And obviously, after playing around with it, it's going to change them quite a bit. But you can see the variety of kind of vegetables and food items we have here. So some of them have peel, some of them get completely destroyed, some of them are fairly rigid, or maybe only rigid if they're of a certain size. So it's a very varied data set that we have here. What we did with that is then to try to learn an embedding, which we can then use for subsequent tasks. So we can sort of look through our data. We can find samples. We can find positive corresponding samples and negative ones. So for example, using tactile or vibrotactile signals, we looked at samples that had similar Mel frequency septum coefficients. And if they were similar, we sort of said, okay, these are going to be positive. And if they were very different, then we said, okay, these are going to be negative. And using a triplet loss, we can then train a network that will take an individual image, give us an embedding, and then we can use that as our representation, sort of much lower dimensional, for performing a classification or regression problem. So here we can see some of the results of this. We have different kinds of ways of defining these triplets. So we have the actual food label. So, is it a carrot? Is it a cucumber? We have some slice parameters. So was this sort of a parallel cut? Was it kind of a wedge cut? We have the audio from playing with the data. So this is our vibrotactile signals. We also have the audio from the cutting itself. So like I said, the robot is performing the cutting itself. We also have proprioceptive. So those are the fingers and the amount of push down. We also have some baselines. So first of all, we have ResNet, the standard off the shelf. ResNet trained a lot of data. And we have a classifier that's just using the play audio. So if we try to classify, for example, the food type, in this case, we had 21 different categories. Obviously, ResNet is going to outperform us. It has a huge training set, so we're not too surprised by that. But we also gave it some other tasks. So for example, we wanted to identify, very hard, very soft, and medium sort of hardness objects. And in that case, ResNet performs fairly poorly. And the best performance is actually achieved when we train our embedding using proprioceptive features. Similarly, if we train, for example, juiciness, so very dry versus very juicy or medium juicy fruits and vegetables, we get the best data or the best representation when we use this sort of vibrotactile playing data. So in this case, we get 46% accuracy. And as you imagine, this is kind of capturing things like those kind of that watery sound of more juicy fruits and vegetables and allowing us to sort of generalize over that. We also looked at slice type and also predicting the width of a slice. So when we close our fingers, how accurate is that going to be? And as you might expect, having a slice-based embedding is going to give us the best one for the slice, and the proprioceptive is the best for the slice width. And so we can see that incorporating these sort of additional sensor modalities in the training is going to allow us to learn better or more efficiently learn classifiers for various manipulation relevant tasks. One picture I always like to show is also this one. So we looked at sort of boiled versus non-boiled foods. So this is effectively embedding that's again being learned for the visual, but it's being trained using these audio features. And we have here these circles, which are these sort of pre-boiled vegetables. And we have these little line sort of structures. I don't know what to call those best. But these are sort of the boiled equivalents. And so what's really fascinating about this is that, for example, we have pears and apples. So we have these orange and pink. And as you can see, before they've been boiled, they're very close to each other. We then boil them, which shifts them over here, and they're still very close to each other in this space. We also have carrots given here in this orange and potatoes, which are brown. And initially, those are actually, there's a clear distinction between the two. However, once they've actually become boiled, they actually move closer together. And if you've ever sort of, eaten sort of a very boiled potato, very boiled carrots, their consistency is actually a lot more closer to each other after you've actually boiled it. And we get this very nice sort of, split between the boiled and the unboiled using simply this audio information. All right, just gonna keep on the time. All right, so the other topic that I'm really excited to be talking a little bit about today is the use of Delta robots for dexterous manipulation. And this is a project that we've been working very closely together with Zeynep Temelon. So many of you are probably familiar with Delta robots from kind of a manufacturing or automation perspective. So these are these very fast robots often used for pick and place. They have 3 motors at the top here, which are sort of moving around this parallel linkage structure underneath. Here you can see it better from the sides. We have 3 degrees of freedom. They're pretty much allows you to control an XYZ position. So we get nice translation control. And one of the great things about these is because the motors are sort of stationary on top, we have a fairly low inertia for the actual end effector. So this is why we can sort of move it around really quickly. Now, this is sort of the classical Delta robot. With new designs, new fabrication, new materials, we can see the emergence of new types of Delta designs. So this is a millimeter scale Delta robot. Obviously, very fast movements that are capable here. I think it's 75 hertz, very accurate. Using piezoelectric, here we have a centerpiece for comparison. And you can see kind of what's done. Again, this is sort of work from Dr. Zeynep Temel, who've been working on this project. And the question that we ask ourselves is, okay, so these millideltas are probably a little bit on the small side for a lot of the kinds of manipulations that we want to do, but can we sort of design a Delta robot that's not that large size, not the very small, but sort of the Goldilocks in between of having about a finger size, right? So a lot of sort of finger designs that we see currently, especially sort of the more anthropomorphic ones, they often have sort of a serial design. So one motor sort of after the other, after another. So you get fairly bulky fingers that have to move all the other motors further down. We also see designs such as the shadow hand, which has sort of a cable drive, so more of a tendon-driven. Obviously, this is very much inspired by human hands, which have a fantastic sort of tendon drive. But for robotics, often there's still a lot of challenges in having sort of long-term control, being very accurate with these tendon drives, because we simply don't have the material properties that we have in the human hand. In many cases, we are interested in sort of this very delicate fingertip manipulation. So, if we're cooking, we can think about rolling things up, about sprinkling things. So we do want to have some kind of an XYZ control over the fingertips. And so we asked the question of, can we actually use a Delta design for a finger? And down here we see a rotational design using a TPU printed parallel structure. But our main design is actually using linear actuators. So this is the Delta gripper. So we have 6 different linear actuators here. Each 3 of those is connected together to create a Delta. We create the parallel linkage out of a single 3D printed part out of TPU, so it's compliant. It can sort of bend, and you'll see it's fairly robust. And then we can attach different kinds of end effectors to the end of this in order to get that sort of, high degree of dexterity. So here we have, 6 degrees of freedom for 2 fingers. It's a very modular design. So we also have a 4-finger design that we're currently building together in the lab. And I'll talk about sort of scaling that beyond that in a couple of slides. So here you can see some of these sort of the dexterity examples. This is kind of a pre-programmed behavior that we have here. So we can pick it up. You can also do some simple in-hand manipulation. So actually rotating the object back and forth. This kind of movement is also very useful. For example, we're trying to extract a grape. So in this case, we actually have teleoperation. We're still working on sort of the algorithms and the control for sort of performing these tasks autonomously. But you can see, we can sort of peel off a grape using these fingers without any kind of wrist motion. And here we have my favorite example, which is the dough rolling. Again, this is currently still being performed with teleoperation, but it gives a good view of the kind of dexterity that these fingers are providing to us. Which is a little bit of a long video, so I'm just going to do the ×10 manually. You can see you can roll it up and then pick it up. All right, so this is a design using effectively 2 fingers. The question is obviously, how far can we sort of push that idea? Like I said, we're currently working on one in the lab, which has 4 fingers. So here's the robustness test. So you can see we can, because it's compliant, we can easily bump into objects. It's very low inertia that we have in our fingers. So, this makes it really nice for interacting with more unstructured environments like we have in the kitchen. So in terms of scaling it up to multiple fingers, what we're currently focusing on is looking into expanding this not into just a gripper, but actually a full array of these manipulators. So you can imagine that this is a hexagonal grid where each one of these small capsules is going to be controlled by a separate delta control robot. So you can see some initial simulation results that we've done on this. So we have, obviously there's a lot of design considerations when working with this kind of a high dimensional system. So here we looked at different kinds of phase gates. So having 180 degrees apart, 3 120, or 4 90 degrees. As we kind of go for more phases, we get this sort of more natural kind of like a rolling ocean behavior. Whereas with the 2-phase, it's very much a step, 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 step. Of course, having the sort of the 2-phase gate also has certain benefits. So if we look at smaller objects, we can easily sort of have objects that kind of fall between the deltas. If we have a high phase gate where only a couple of them are in contact at any point, whereas with the 2-phase gate, that becomes a little bit more robust. What we're very excited about is also the different kind of strategies that this kind of a system would afford. So here, for example, if we put up a bunch of fingers to create like a wall structure, we can use that to align objects. There's an ability to do kind of more in-hand manipulation. So this kind of a manipulation potentially. And so we're very excited about working on this sort of delta array. So far, we've been looking at some of the strategies and simulation, but Zeynep Temel and I are currently we just got a master's student who's going to be focusing on developing one of these arrays so we can explore some of these on the real world and do some exciting tasks such as maybe rolling out dough or something like that with a lot of different fingers. So with that, I want to thank all of my students and obviously Professor Zeynep Temel, without whom this sort of Delta robot research would not have been possible. Definitely recommend looking to her research as well. And with that, I'm at the end of my talk. So we looked at sort of vibrotactile sensing and using that for identifying different kind of materials. We then also looked into using that kind of information to learning visual representations. And finally, looking at Delta robots as a sort of very dexterous design for fingers. All right. Thank you very much.
Okay.